And now we're going to discuss the second Latin extension theorem. It's a bit more complicated than the first one. So it's going to rely on some definitions to set things up. So let L be a Latin rectangle shape P by Q. And again with entries as usual. Set N of size little n. Okay, then so for K, one possible entry K, we put this way, ML of K is the number of occurrences of K in L. Okay, so we look at how many times we see a K in the full table of entries of L, and we note that this is actually the same as the number of rows of L that contain K. Okay, that's because this is L is supposed to be a Latin rectangle. So if a row contains K at all and it only contains it once, we're not allowed to have any repetitions in any row. So any row that contains K contains precisely one K. So the number of K's is exactly the same as the number of rows that contain K. And of course, that's also the same logic works for columns. Okay, and then we define ELK. Oh, and that's just the terminology. That's the multiplicity of K and L. Okay, and then ELK is MLK plus N minus P minus Q. Okay, so this is what we're going to call the excess of K in L. Okay, so so that's what we mean by the excesses, and then we're going to say L is extendable if let's say we can add extra rows and columns to make an n by n Latin square. Okay, so in the previous video we proved that if L has maximum possible width, in other words, if Q is equal to N, then it's extendable. You can always add extra rows to make it a Latin square, and by a completely symmetrical argument, if P is equal to N, if it's got maximum height but not maximum width, then you can still just add extra columns to get a Latin square. So in those cases, it's extendable. But the case we're really interested in is where both P and Q are strictly less than N, so we don't have maximum height or maximum width, and then it's less obvious whether we can do the extension. And so the theorem is L is extendable if and only if ELK is greater than or equal to 0 for all K. Okay, so notice, so we add N and subtract P and Q. That could force it to be negative, but so there'll be some examples where some of these excesses are negative. But if ELK is greater than or equal to 0 for all K, then it turns out the thing's extendable, and vice versa. Okay, let's prove the easy direction as a separate lemma. So if L is extendable, then ELK is greater than or equal to 0 for all k in it. Okay. So it's kind of the usual way around. Yeah, we've got this kind of numerical criterion, and then we've got this criterion for existence of some kind of complicated combinatorial object. And typically it's easy to prove that, you know, if the existence thing holds, then the numerical criterion holds, and then the real work is to go the other way around. Okay, so we're assuming that L is extendable, so we can choose an extension. So that's going to be like this. We have our original L. That's kind of P rows here and Q columns there. And then we fill it out to a square. So we have to add n minus Q extra columns and n minus P extra rows. And so we've got some block L prime here. Call this block L double prime. This one here L triple prime. And actually we really don't need to say anything about L double prime or L triple prime. We just consider the top half of this extension. Okay, so let's put L upper star is just the top half. So this is Latin so it's shape P by N. Okay. And now now remember, K has got to appear once in each row. Of L upper star, right? So yeah, that's because, you know, L upper star, the rows have length n, so each row has n distinct entries taken from the set capital N of size n. So every element of capital N must appear precisely once in each row. In particular, this K has to appear precisely once in each row. So that, in other words, the multiplicity in L star of K, okay, well, you get to 1K in each row, and there's P rows. So that's equal to P. So in other words, but the multiplicity in L upper star, of course, is the number of times you see the K in L plus the number of times you see it in L prime. So we see that MLK plus ML prime K is equal to P. Okay. Actually, so let's just say that slightly differently. That means that MLK is P minus ML prime K. But if we look at ML prime, I mean, how many times could K appear in here? Well, K can only appear at most once per column. At most 1K in each column of L prime, so the total number of Ks is at most the number of columns, which is n minus Q. So we've got an upper bound of ML prime K is less than or equal to n minus Q, but we're subtracting ML prime, so that changes the direction of the inequality around. So we get this is greater than or equal to P minus this n minus Q. which is P plus Q minus N. Okay. And therefore the excess in L of K, which is MLK minus P plus Q minus N. That was just the definition of the excess. So that's, and we know that the ML is greater than or equal to P plus Q minus N, so that's greater than or equal to 0. That's claimed. Okay, so that's the easy half of the theorem we stated, that if L is extendable, then this numerical criterion holds. Okay, so we stated a theorem and we proved the easy half already. Now we need to talk about proving the hard half. But so for that we're going to use one of these applications of Hall's theorem that we mentioned previously. So let's just recall that. Okay, so so we're going to consider a so we have column sets Cj, so these are subsets of A for J and B, and corresponding row sets Rk contained in B for K and A. Okay. Now let's suppose that there's some constant d greater than 0 with the in this case we're going to assume that all the candidate set, all the column sets Cj have size exactly d, and the row sets Rk have size less than or equal to d, so and we're going to suppose these row sets have size less than or equal to d for all k in the set A. Okay. Okay, so then we claim there is a solution so formally speaking, a solution for this matching problem, we have some candidate little cj and capital CJ. So in the kind of job application setting, this is CJ as the person who's given job J, and these have to be distinct, and they have to lie in CJ, so which means that they're qualified. But yeah, we had this application in which there was this auxiliary condition. For each k with mod Rk equal to d, k appears as one of these things. So remember, this was in this sort of job allocation setting. What we said, these size of Rk is less than or equal to d. It means if person k can do at most d jobs. The people for which size of Rk is equal to d, so they can do the maximum number of jobs, we call those the talented people. In that language, the conclusion was that we could do an allocation in which every talented person gets a job. And so here that's what we've just translated in a slightly more abstract language. If k is a person with mod R, or if k is an element of A with mod Rk equals d, corresponding to talented person, then k is in the set of assigned things. Okay, so that was so this is a fact that we proved previously. Okay, so that's going to be a key ingredient in the induction step for this Latin rectangle extension thing. Okay, so now we're going to suppose we're given our Latin rectangle here. So it's P by Q again. Okay, so we're going to prove this lemma, which says that if ELK is greater than or equal to 0 for all k, then so we can add a row to make a P plus 1 by Q Latin rectangle L prime in which we again have EL prime K greater than or equal to 0 for all K. Okay, so we can add add one row and still maintain this extra criterion that all the excesses are not negative. And of course, if we can prove this lemma, then because we've propagated this condition that the excesses are non-negative, we can just do the same thing again and again until we've got something of maximum height. Okay, but for the moment, we're just going to consider problem of adding a single row. And so so A is capital N, the set of potential entries, the kind of things that we're using to fill up the table, and we're going to take B to be the set of columns. Okay, and then again, as we did in the last proof and in the previous video, Cj is kind of possible entries in position P plus 1 J. Okay, so here's our new row, and then we're looking in this is like 1 up to Q across here, and this is our jth column, and we're looking at the possible entries that can go here. And so this is kind of exactly the same as in the last proof. The potential entries here, there's n minus the number of things above here, and there are p things above there, so that's n minus p. Okay, so that's good. And then rk, okay, so that's this is a that's the set of columns where k is allowed. So mod rk, so that's going to be that's going to be the total number of columns, which is q minus number of columns already containing k. So okay, so but the number of columns that already contain k, so that's q minus that number of columns already containing k. That's just the number of k's that we've got, as we mentioned previously, because if a column contains a k, then it only contains precisely 1. So this is q minus the multiplicity of k at L. Okay, but we're given that that ELK is non-negative, but ELK, remember, is MLK plus n minus p minus q. And just rearranging that slightly, that gives us that q minus MLK. We just shuffle this around a bit. That's going to be less than or equal to n minus p. Okay. Okay, and so, and in fact, these are going to be equal if and only if the excess is precisely 0. Okay, but anyway, we see that the condition we can take d to be n minus p, and so we've seen here that so we've got that the column sets Cj have size precisely d, and these row sets Rk that have size q minus mlk, which is less than or equal to d, and we see that the proposition is applicable. Okay, so the proposition we wrote on the previous screen, the hypotheses were that the column sets Cj had size equal to d, and the row sets Rk had size less than or equal to d. So, so the conclusion of the proposition that we mentioned the conclusion of the proposition we mentioned involves this set T, which is a set of K for which the row set Rk has size equal to D. And the calculation on the previous screen, we see that mod Rk equals D if and only if the ELK is equal to 0. Right, we proved that in checking the condition that mod Rk is less than or equal to D, we used the fact that ELK is greater than or equal to 0, and just looking back at those formulae, you see that this is just going to be an equality if and only if this thing's an equality. Okay. So what we conclude is that we can add a new row, say C1 up to CQ to L, to give a new P plus 1 by Q Latin rectangle. And we can also ensure that every K with ELK equals 0 appears in this new row. Okay. And that was what the conclusion told us. It said that these were kind of corresponded to talented people. Every talented person gets a job. People appearing in this new row are the people who get a job, as it were. So we conclude that all these entries with ELK equal to 0, they're all going to appear in this new row. So this extended thing we're going to call L prime. So what's ML prime K? So that's going to be MLK plus 1 if K appears in the new row. And just equal to MLK if K does not appear. So EL prime K, what's that? So that's ML prime K plus N minus P plus 1 minus Q. Remember, L prime as the shape of is P plus 1 times Q. So to calculate the excesses now, we have to add N and subtract P plus 1 and Q. Okay. So we're kind of subtracting an extra 1 here. So by comparing with what we've got here, if K does appear in the new row, we get a plus 1 from here and a minus 1 from there, and it doesn't change at all. So we get ELK if in the new row, and ELK minus 1 if not. Okay, so so we want to check that these excesses are still greater than or equal to 0. Okay, can EL prime K be negative? Well, so how can this be negative? Well, you have to sort of, if this ELK was strictly positive, then you'd still be okay either way around. The only way you can get something negative is if ELK equals 0 and K not in the new row. But that doesn't happen by what we wrote here. Okay, every K with ELK equals 0 does appear in the new row. Okay, so we've done what we needed to do. We've added a new row, and it still has the Latin property, and we've also ensured that these excesses EL prime K are still greater than or equal to 0. Okay, because some excesses may have dropped down by 1, but only the ones that were already strictly positive before, so we don't get anything negative from that. Okay, so we've shown that if we've got a Latin rectangle in which all the excesses are non-negative, then we can add a new row. And as a corollary of that, with ELK, okay, we've got a P by Q Latin rectangle with all the excesses non-negative, then can repeatedly we can repeatedly add rows, ensuring that the excesses will stay non-negative the whole time until we've got an N by Q Latin rectangle. So that's a maximum height. Then then the first extension the first Latin extension theorem says we can add columns. Okay, so actually the way we formulated the first Latin extension theorem, we said if it's got maximum width, then you could add rows. But by essentially exactly the same argument, or just by kind of transposing your Latin squares backwards and forwards, it works equally well that if you've got something of maximum height, then you can add columns to get an n by n Latin square. Okay, and so that was the hard direction of the second Latin extension theorem. You've got a Latin square of any size in which the excesses are all non-negative, then it can be extended to a Latin square.